Okay, sorry about that. So we'll go ahead and we'll get started. So last time at the end, sort of rushed over some things with algebraic closures and algebraically closed fields. So I want to step back and try that again and finish constructing an algebraic closure in general, but also state some things a little bit more carefully. So let me give two very closely related definitions first. Okay, so the first is an algebraically closed field. So a field K is algebraically closed if any polynomial, any non-constant polynomial, in fx and kx has a root in K. So f of little k is equal to 0 for some k in K. So a field is algebraically closed when any non-constant polynomial has a root. Let me leave some room, but write down the example down here. So the example we talked about last time was that the complex numbers are algebraically closed. I guess this is not a new thing for you, but I just want to sort of say the definitions carefully because I didn't last time. And we talked about last time how you could sort of prove that using Liouville's theorem, for example, if you want to give an analytic proof. You can also give algebraic proofs, although we probably won't. Okay, so a field's algebraically closed if any non-constant polynomial with coefficients in K has a root in K, or equivalently, you could instead say splits in K, splits into linear factors. Which means right as a product of linear factors in K of x. So why is this equivalent? Well, if it splits into linear factors, certainly it has a root. On the other hand, if you can find one root, then you can just sort of divide out by the corresponding linear factor, and you have some new polynomial, and that one also has a root, and so you just repeat until you sort of get your factorization. Okay, so that was the first definition. And then the second definition is an extension L over K is an algebraic closure. So this one I did define last time, but let me just say it again. Because when I defined it last time, at some point I sort of started to misspeak and then caught myself. But anyway, probably there's a good chance I confused anyone who already knew what they were talking about. So let me try again to state it without misspeaking. So an extension L over K is an algebraic closure of K if every polynomial, so if two things happen, so I'll call this Roman 1 and Roman 2. So the first is every f in K of x splits into linear factors in L of x. So another way of saying that is just f has the same number of roots as its degree, sort of when you count them with multiplicity in L. 2, L is algebraic over L is algebraic over K. So this sort of second condition is sort of some sort of minimality condition. Okay, so good. And when I misspoke is sort of, I started to say, at some point when I introduced this, I started to say that this was equivalent to saying sort of any f and k of x had a root in there, but I'm not actually sure if that's true. And anyway, sort of what I had in my mind was the definition of an algebraically closed field, not of an algebraic closure. So for an algebraic closure, better to sort of put in the definition that sort of every f splits over L. So all its roots are defined over L somehow. Okay, good. Okay, so there's a definition, and there's a grammatical sort of relation between these two that sort of suggests a mathematical relation. So, and you should guess that an algebraic closure is algebraically closed, and that's true. And then we also sort of saw a result. So what we finished last time with was a result going in the other direction. So let me sort of say this just all as a lemma. So this includes the statement we had last time, but also something extra. So first part is the extra, so that we didn't talk about last time. This says if k bar over k is an algebraic closure, so that's a statement about polynomials with coefficients in k and their roots in k bar. Then, yeah, so k bar is sort of the common notation for an algebraic closure. And again, there's no uniqueness to an algebraic closure, but so algebraic closures are unique up to isomorphism. But okay. So k bar is algebraically closed. So, okay, so this is the thing we didn't talk about last time. So that's sort of going from a statement about polynomials over k and their roots in k bar to polynomials of coefficients in k bar and their roots in k bar. So this is sort of somehow this k bar being algebraically closed is a strictly stronger statement than sort of k bar over k being an algebraic closure. So what this says is sort of another way to sort of define an algebraic closure is it's an algebraic extension which is algebraically closed. So maybe depending on the source, you might sort of see that definition instead. Okay, good. And then the second statement, so this is something we talked about last time. So we said if, but we didn't say it in these words. Let me say it now in these words. If L over K is any extension, such that L is algebraically closed, then, so I can make an algebraic closure of K living inside of L just by taking all of the algebraic elements. So K bar, which sort of just is as defined, it's just a subset of L, which is all the elements little l and L in the field L, such that little l is algebraic over K. Okay, and then so that's the definition. Then the statement is this is an algebraic closure. Okay. So again, we proved this at the end last time. Let me just remark on how that went. This is the second part. The point was, clearly this thing is going to be algebraic over K. Sort of by definition, you're only taking elements which are algebraic over K. Well, it's an algebraic closure over K because sort of if you take any polynomial of K, because if you take any polynomial in K and then take with coefficients in K, then it has a root in L. That root in L is sort of by definition algebraic over K. So it sort of lives in this subset K bar. So the only thing you actually had to check here was that K bar was a field. And so for that, you have to check sort of like alpha plus beta is algebraic, then sort of there's alpha and beta are algebraic, and like alpha and beta, alpha plus beta, alpha times beta, and so on are also algebraic. And so the way we justified that was using that sort of K adjoin alpha and beta was a finite extension. And sort of finite extensions are automatically algebraic, and sort of alpha plus beta and alpha times beta and alpha inverse, beta inverse, and so on all lived in that finite extension. So that was the idea for the second part. And let me just add to this lemma something. Well, okay, I'm gonna leave it like that. Okay, so also write proof. So 2 was last time, and 1 I'll sort of just leave as an exercise. I mean, the idea is very similar to how we proved 2. You want to use the fact, and you want to sort of use the fact that any polynomial over K has a root, and then, well, how can you use that to show that any polynomial over K bar has a root? Well, like if you start with a polynomial over K bar, just form some extension where it has a root, some finite extension. And then you can sort of check that like that finite extension of K bar is sort of going to live. Wait, so you can check sort of the if you can sort of take a root in that finite extension is sort of living in a finite extension of K. So what you're going to use is sort of that each of like if you take a polynomial in K bar, well, its coefficients actually live in a finite extension of K. And so that's sort of how you can argue this first part. So let me say the hint. Let me write down. So if you have some polynomial with coefficients in K bar, then you can look at the subfield generated by those coefficients. This is finite over K. Okay, and then you can argue from there. Okay, and so good. So that's the statement. And so, well, this just tells you. This tells you sort of these words the words we've chosen for the names we've chosen for these definitions make grammatical sense. So if the algebraic closure of a field is algebraically closed. I think that's sort of the main part of 1. And then 2 is sort of a little more powerful because 2 is something we can use to actually produce an algebraic closure. 2 is this thing I sort of mentioned last time, which shows that if we want to sort of show any field has an algebraic closure, then we don't need to sort of produce an algebraically closed field on the nose. We just have to sort of produce any field, we don't have to produce an algebraic closure on the nose. We just have to produce sort of any algebraically closed field that contains it. And so the example of how that worked so if I take Q bar, which is just all sort of the complex numbers that are algebraic over Q. So just again, that means it satisfies a polynomial of coefficients in Q. This is an algebraic closure of Q. Because we just use part 1 or part 2 plus sort of C algebraically closed, which again, you can prove using Liouville's theorem. So you can prove that using complex analysis. Okay. So this gives you sort of a nice way to produce an algebraic closure of Q without sort of having to make any abstract arguments. It's useful to know that algebraic closures exist. So let's go ahead and prove it. And the proof is sort of fun and illustrates. We're going to do the proof because the proof like illustrates how like thinking about how fields arise in ring theory is useful even for sort of constructions that seem internal to field theory. So let me state the result. The theorem is K is a field. So I stated this last time, but let me say it again. If K is a field, then there exists an algebraic closure K bar over K. So in particular, that's an algebraically closed field containing K, but it's an algebraically closed field containing K with the extra property that it is itself algebraic over K. So like the complex numbers was an algebraically closed field containing K or containing Q, but it's sort of has transcendental, like complex numbers contains elements that are transcendental over Q. For example, pi is transcendental, although that's a little tricky to actually prove. There are sort of numbers, there are real numbers that sort of simpler to prove are transcendental, or you can use just a cardinality argument to show there are many transcendental numbers, many transcendental complex numbers. So here, when I say there's an algebraic closure, I don't mean that there exists something like C that's sort of algebraically closed, but like possibly transcendental. I really mean there's something like this Q bar. So it's algebraically closed and algebraic over K. Right? And what this lemma told us is that to produce such a thing, it suffices to find any algebraically closed field containing K. So then that was almost all the statement of the theorem. So there exists an algebraic closure K bar over K, and it is unique up to isomorphism. So that means if you take two different algebraic closures, then there is an isomorphism between them. That isomorphism is not unique. Like, and there's nothing about what I've said that pins down what that isomorphism has to be. And usually there are many different choices of isomorphism. Let me recall an example we already talked about. So the complex numbers is an algebraic closure of the real numbers. And so is R brackets X mod X squared plus 1. But there are two different isomorphisms of those extensions. So I could either send sort of X. I could send X to I, or I could send X to minus I. So in algebraic closures are sort of unique only up to isomorphism for essentially the same reason that splitting fields are unique only up to isomorphism. So in one way to think about algebraic closures is sort of you took splitting fields for all polynomials and then sort of just found a way to put them together into one big extension. And that's actually one way you can prove this theorem. So, and if you try to prove that theorem, you sort of run up against this issue that there is no canonical isomorphism between splitting fields, but nonetheless, I mean, I think you can sort of, well, you can sort of set it up to sort of do it one step at a time and then apply Zorn's lemma, and you can sort of produce a proof that way. So that's one way you can do it. And probably like if you took a field theory class, like if you discussed existence of algebraic closures like in an undergraduate class, that's maybe the way you did it. Dummett and Foote gives a nicer proof. The statements, let's talk about this nicer proof of sort of existence. I mean, I don't really want to somehow, like, once you know they exist, then proving they're isomorphic is not so hard, and like basically uses the thing I just said. Sort of you sort of look at sort of larger and larger subfields and sort of pick isomorphisms. So you have to pick this in a compatible way, but well, you can. So the main thing is to sort of get existence. And so again, so by the lemma, it suffices to produce any algebraically closed field L containing K. Because once we have some algebraically closed field, we can just take sort of the subset of algebraic elements, and that gives me an algebraic closure. Like, again, just like we did to sort of produce this Q bar, this algebraic closure, this Q bar, which was an algebraic closure of the complex numbers. So we're just doing that. And the only difference here is, like when we start with Q, we had the complex numbers, and like, so that algebraically closed field was just sort of handed to us by our past knowledge in mathematics. I mean, if I start with a completely arbitrary field K, like I don't have some sort of fixed algebraically closed field containing it that I just happen to know about from my sort of past work in mathematics, like sort of my past undergraduate work in mathematics. So you actually have to do something to produce such a field. Well, okay, so there are choices. I already said you could sort of build it up from the bottom, sort of using sort of Zorn's lemma, if you're careful, but it's hard to be careful in that argument. Or we can sort of, we can do something to build a really big thing. So we're gonna do something that builds sort of some really big thing, but is particularly algebraically closed and contains K. And then, at least, and maybe it's not actually really big, but sort of our construction will sort of look pretty big. And then there are other ways you could do it. Like you'd probably, for example, if you know what an ultra product is, you could probably come up with a nice proof using an non-trivial ultra product. But this is sort of beyond the scope of what I want to talk about. So okay, so what are we going to do? Okay, so I have this field K, and I'm going to just look at the set of irreducible polynomials over K. Okay, well, if I want all of these to split, I'm at least going to need them all to have a root. So, well, let me start by just sort of producing some ring where these all have a root. So I'm going to look at the polynomial ring in infinitely many variables. So I have a polynomial ring where the variables are indexed by the irreducible polynomials in K. And then I'm just going to mod out by the ideal. I'm going to mod out by the ideal generated by f of xf for sort of all f and s. So this is the same thing we do to like add a root of a single polynomial. Like if we want to add a root of a single polynomial f, we just do k brackets x mod f of x. And that sort of then x becomes like in that field, like in that ring, x becomes a root of f, so tautologically. So the only difference here is we're doing it for all of them at once. The issue is, like you might think now we're done, and the issue is this might not be a field. And this is a ring, certainly this is a ring, because so I took a polynomial ring and modified by an ideal. But there's something a little bit subtle going on when I'm doing this for more than, even for two polynomials at once, like this might not end up being a field anymore. Like if I took two irreducible polynomials, there's no reason this would be a field. Like for example, like if you took the same polynomial twice, you wouldn't get a field. So this is a ring. Okay, so this is a ring containing a root of f for every irreducible polynomial f. Okay. But when I can just take a quotient of this, so like if I want a ring, like I want a field, but I have a ring. So well, let me just take a maximal ideal. So take a maximal ideal M of R, and look at sort of an R mod M is now a field containing K, and this still has a root of all F. So this still has a root of all irreducibles. Because I mean, certainly if there was a root already in R, like there's a root in R mod M for any ideal. So taking this maximum ideal, so yeah, so let me call this K1. This is R mod M. So taking this maximum ideal, this, I mean, you're using that sort of, this uses the fact that any ring, any non-zero ring contains a maximum ideal. So that statement uses Zorn's lemma. And then no matter which proof you write down, you're going to use Zorn's lemma somewhere. So here, the sort of packaging of Zorn's lemma is in the existence of a maximal ideal of this ring I constructed, so just by fiat, containing a root of every polynomial, of every irreducible polynomial. Okay, good. I mean, there is sort of one little thing I brushed over. And here you need R to not be the zero ring. I.e., like you need this ideal you quotiented out by to not be the whole ring, it's the whole polynomial ring. So this, I mean, it's not totally clear from just what I wrote down that this is not, like this ideal is not just a whole ring. Okay, so, okay, so let me just say that's an exercise. And this is sort of a basic, this is a basic exercise related to a lot of the things you guys would have done when you were talking about like algebraic geometry and the null-Ansatz and sort of related things last time. So, and something very similar will shown up already, but more difficult than this, depending on sort of how you prove the null-Ansatz. So show this. And the hint is then if not, sort of write so just write one as linear combination. And so this only uses finitely many variables. So this thing sort of looks like you need to sort of make some argument about infinitely many variables, sort of reduces to something with only finitely many variables. This thing with only finitely many variables, like, well, there's still something to do, but I think probably you can come up with a contradiction or sort of see that this violates some other fact you know in this case. And this proof is written down in dumb input, so if you get stuck here, you can always look it up. Okay, but sort of once you've checked that point, then you really get a maximal ideal M, like a non-trivial maximal ideal in this non-trivial ring, and then you get this field K1, which has a root of all irreducible polynomials. So K1 contains a root of every irreducible in K, in Kx. Okay, I mean, K1, there's no reason it has to be, and nothing I've said says that K1 is algebraically closed or that it's an algebraic closure. I mean, nothing about what I've said says that K1 is even algebraic over K, like K1 sort of can be transcendental, so it could in principle be transcendental. Probably is transcendental, sort of, except in very trivial examples. So this K1, I mean, it's not an algebraic closure of K. It's not algebraically closed, typically. And these, at very least, sort of nothing I've said would verify that, but it does contain a root of every irreducible in K brackets X. And so, well, now let me just repeat. So sort of, let me just do the same thing to K1 to get K2. So now I'm going to take all of the irreducibles in K1, then sort of make this ring, add the roots where I get roots, and then sort of take a maximal ideal, and I get some field extension where all the irreducibles in K1 have roots. I mean, why is this better? Like, well, now if I sort of start off with an irreducible in K brackets X of like degree 2, like now it actually splits completely, because sort of first I was sort of picked up one root and then sort of, okay, or like it was a degree 3. Like first I picked up one root and then maybe I had a degree 2 factor left, but that sort of picked up its roots when I picked up the next root when I went to K2 and so on. So, and I just keep on going. So you get K1 containing K2, containing so on. And so it's relatively easy to see if f of x is in K brackets X of degree n, then it splits completely in Kn. I mean, really in the way I've set the numbering in Kn minus 1 even. So I'll say K0 is equal to K. So degree 1 thing already splits in K, degree 2 thing will split in K1 because you've added a root. So once you add a root to the degree polynomial, it's all of them, and so on. Okay, so good. So then I'm going to write L to just be the union from I equals 1 infinity of Kn and of Ki by from I equals to 0 infinity Ki. And this is a slight abuse of notation because this is a common abuse of notation. I hate this abuse of notation, so that's why I'm sort of calling it out. Because like a union takes place in an ambient set. So, but like exactly what I'm looking for is some ambient field that contains all these things. So like, it doesn't really make sense to write union here. I mean, it's a common abuse of notation, but like, and this is really sort of, and it's better to call this a colimit of Ki. And so colimit just sees, okay, even though this isn't really the union, like, well, okay, and again, I guess it's not an abuse of notation, sort of depending on how careful you are. Like if you're sort of, yeah, and I guess sort of like set theoretically, it's not abuse of notation, but somehow field theoretically, it's an abuse of notation. So I sort of prefer, and when I'm taking a union of two things, like I don't really want to be taking sort of the union. Yeah, okay. And somehow, okay, so and you either, yeah. On the one hand, this is an abuse of notation, but on the other hand, like if you don't think this is an abuse of notation, then you have to explain why it's a field. So I prefer the notation that sort of implicitly says you have to explain why it's a field. Okay, and if so, this is not helping anyone, that's fine. You can think about it. You can think about sort of why I'm confused and confusable later, and hopefully make yourself less confused and less confusable than I. Okay, so anyway, I mean, so the point is, so okay, this is a field, and this is an algebraically closed field, actually. So the point is sort of, if f is an L of x, so if f is a polynomial x, well, then the coefficients, and there are only finitely many of them, and so they're all sort of contained at some finite step. So these are all contained in sort of ki for I sufficiently large. So really I can think of f as being contained in sort of ki as a polynomial of coefficients in ki, but then f has a root in ki plus 1, which is also contained in L. Okay, so L is algebraically closed. So that gives you, but this is what we needed. We needed some algebraically closed field containing K. Yeah, well, anyway, I think this is a really fun argument. Yeah, maybe after doing it, I'm not sure I expect you to agree with me, but I just think this is sort of really a nice illustration of how you can sort of combine some algebraic ideas to make an elegant argument, sort of about the existence of something. Okay, good. So that establishes most of the theorem, and then, well, unique up to isomorphism. So that establishes the existence of algebraic closures of arbitrary field. And while unique up to isomorphism, I'll leave that as an exercise. Okay. So let me make one more remark about terminology, then we'll take a break, and then we'll sort of do something much more concrete. Sort of splitting fields are not unique. In the sense, sort of, they're not unique in the sense that there are multiple splitting fields, but they're all sort of differ. Well, let me say it this way. So they're unique only up to isomorphism. This is something we've seen before. But and this non-uniqueness is often, so it's often a conceptual issue, and so sometimes even like a logistical issue when you're writing down a proof. So, and often it's sort of it's often nice if you can sort of have some way in hand to sort of have a unique splitting field and sort of be able to talk about like sort of the splitting field of two different polynomials, like, and relate them. So here the but is like, if you fix an algebraic closure k bar over k, or in fact, just or any algebraically closed extension. So for example, like if k was q, you could also, instead of k bar for what I want to say, you could take k, you could take the complex numbers. Then so for any f of x with coefficients in k of x, there is a unique splitting field of f sort of in k bar. So when I say unique, that means is like, if you don't have sort of some ambient extension fixed like this, then like the words the splitting field don't make sense because there is no sort of pinned, like specifically pinned down splitting field. So if you want to sort of pin down a splitting field, then you really, if you want to pin down a splitting field, like you need to do something, and like one thing you can do is sort of fix an algebraic closure. So I mean, if I have some, So it's like when I say in k bar, I mean sort of it's a subfield of k bar. So it's just, and it's just given by the root of k, sort of alpha 1, alpha n, where alpha I inside k bar are the roots of f. The splitting field is always sort of generated by the, like, if you take the splitting field of f, it's always generated by the roots of f inside that splitting field. And here you're just saying sort of if you have some ambient algebraic closure, like you can just sort of think of those roots as living in the algebraic closure, and then sort of it generates some subfield, and that is the splitting field of f. So, well, and I think various sources are sort of to various degrees guilty of like not being careful about saying the splitting field versus a splitting field. Like, well, I mean, it never matters, and it doesn't really matter, except sort of you can get yourself in sort of a conceptual knot, and so you can actually, you might sort of get confused if you're not careful. But and so anyway, this is a very, I mean, this is a very convenient trick to have up your hand to sort of make sense of the words the splitting field. And in particular, like if you want to sort of like, and this gives you a way to make sense of like the compositum of the splitting fields of two polynomials. Like as long as you're working in some fixed ambient extension, you can take the compositum. So if you have, like, you can take the compositum of the splitting field of f and the splitting field of g inside this fixed k bar. So anyway, this is a good way to sort of eliminate some of that ambiguity. But of course, I mean, like what you're doing when you do that is you're just sort of you're making all of your choices at once. Like you're just sort of somehow choosing an algebraic closure is like fixing all of these choices of isomorphisms between sort of splitting fields in some sense. Like it's essentially like fixing algebraic closure is somehow like equivalent to giving the data of a distinguished splitting field for every polynomial. Okay, let's take a pause there. Let's come back, say at 1:15, and then we're going to do, and this was like about as abstract as we're going to get when we're doing field theory. And now we're going to get about as concrete as we're going to get when we're doing field theory. So we'll come back at 1:15. Okay, so new topic, although if we make it, we'll touch back on algebraic closures before we finish today in a very specific case. So we're going to talk about finite fields. So, well, a finite field is just a field with finitely many elements in it. So the size of f less than infinity. Well, but we already know something about this because on your homework and sort of / in class, we showed that that means the size of f is some power of p, where p is the characteristic of f. And the point was, if your prime subfield is the rational numbers, then the field is infinite. So the prime subfield has to be fp, i.e. the characteristic has to be p for some prime p. And then, well, if you're finite, you're in particular finite dimensional over fp. And so you're a finite dimensional vector space over fp, so you have size some power of p. Okay, so any finite field f is an extension, is a finite extension of fp. So it's something we'll use. So yeah, let me just repeat what I said. The size of f is just p to the degree of that extension. The dimension of f as a vector space over fp. Okay, so that's what a finite field is. I mean, what I haven't told you, and what we haven't discussed so far, is whether or not finite fields exist besides the ones we already know. So we know about fp, but again, well, there's some content to the question of like, is there a field of order p to the n for every n? And well, let me leave with the punchline. And yes, there's a field of order p to the n for every n, and it's unique up to isomorphism. But we'll get there in a minute. And this is actually not, this is not hard to see. Well, there are many different ways you can justify this, but we've done enough now that there's a very simple way to justify this. But before we do that, let's just do a quick exercise. So I'll give you all maybe 3 or 4 minutes to construct a field with 4 elements. The size of F is 4. Yeah, so let's say 4 minutes to do that, and then we'll pick up. So everyone can just think about it on their own. And well, if you quickly construct one with 4 elements, sort of keep on going up powers of 2 and see how high you can sort of construct them. Be explicit. Okay, can anyone volunteer either in the chat or out loud a construction? Good. So the chat, someone just posted F2 join X mod X squared plus X plus 1. Okay, good. So, well, why is this a field with 4 elements? Well, it's a degree 2 extension of F2. I mean, so X squared plus X plus 1 is irreducible over F2 because it has no roots. So F2 is Z mod, sorry. I've said that, I think I've used this notation already, but let me just remind that F2 means Z mod 2Z. So it's the field with 2 elements. So this is irreducible over, this polynomial is irreducible over F2 just because it doesn't have a root. So a degree 2 or degree 3 polynomial over any field is irreducible if it has no roots, just because like if you write down all possible types of factorizations, like you're always going to have a linear factor if you factor non-trivially. So if you want to check whether it's irreducible, it's particularly simple because you just have to check there's no roots. Well, if I evaluate 0, I get 0 plus 0 plus 1, which is 1. And if I evaluate 1, I get 1 plus 1 plus 1, which is 3, which in Z mod 2Z is 1. So also non-zero. So this is irreducible. Excuse me. So this is irreducible over F2, and thus, okay, well, thus it is. This is a degree 2 extension, and so if I write, so this is F. I'll call F sub 4. So the size of this is 2 squared is 4. Okay. So, and how could you do this? How could you reverse engineer this? I mean, if I ask you to construct a field with 4 elements, you say, well, 4 is the power of 2, so this is going to have to be an extension F2. So I haven't been given anything here, so I only really know one way to create extensions of F2. It's to come up with irreducible polynomials and sort of take the sort of natural construction that gives me an extension with a root. So this is sort of how you can arrive at this example. Okay, so let me state a result that will be very useful. in characterizing and constructing finite fields. So if F is a finite field, then F cross, so this is the group of units in F. So and this makes sense for any ring, but here F is a field, so the units are just, you take F and you remove the 0 element, and then the group law is multiplication. This is a cyclic group. And well, cyclic of order, just its size. I mean, so the size of F cross in this case is just the size of F minus 1. Again, because we threw out 0. So this is actually a very, if you see this lemma in the wild, you might not know what theory to invoke to prove this, and then it could be difficult. But since we're in sort of a field theory class and talking about roots of polynomials and whatnot, and before that we talked about group theory, and somehow you can meta deduce how you're going to prove this thing in a simple way. And so the point is, okay. Yeah, there are slightly different ways to do this. Let me do it this way. So let me recall and I'll recall it in a particularly simple way to verify. If A is a finite abelian group, with at most n elements of order n for every n, then A is cyclic. So, and this is true without the words finite, without the word abelian group, but it's particularly easy to verify for an abelian group because you can just look at the classification of abelian groups. Okay, so this is an easy exercise to verify if this isn't sort of immediately familiar to you. It's yeah, okay. And it's related to some other characterizations of cyclic groups. This is the criterion we're going to verify, and we're just going to observe. So if some little f and big F, or that's probably, we call it just A, and I'll call it A. So if A is an element F cross, such that A to the n is equal to 1 in F cross, so 1 is the identity in this group, then A is a root of x to the n minus 1. In polynomials of coefficients in F. But I mean, this is degree n, so it has at most n roots in F. Well, in particular F cross. I mean, 0 is not a root of this though, so all the roots are going to be in F. Okay, so we're done. Every element satisfies A to the n equals 1. Because this group, let me say it this way. This is a finite abelian group, and the elements of order n are exactly the solutions to A to the n equals 1 in here. But all of those are roots of x to the n minus 1. So in this field, and so we know there are most n of them. So this condition is verified. Another way to say sort of the main observation here is that because F is a finite field, all of any non-zero element is torsion in the multiplicative group. So any non-zero element is a root of unity. So the roots of such a polynomial are called roots of unity. And so and finite fields are special because everything non-zero is a root of unity. Okay, good. So that's this. And then let me also remark that this proof generalizes a little bit. So you can say, so if you have any field such that somehow the point in any field, the sort of torsion elements in F cross are just the roots of unity. And so in particular, and so somehow for any field, if the torsion elements in F cross is a finite group, then it's a cyclic group. Okay. But anyway, we just need this for finite fields, and this is the main place it's useful. Okay, so then we'll use this to prove our main theorem. Let me state the theorem, and then yeah, I'll state it sort of as this precise result, but I'll include also the in consequence of it. So I have a field I have an extension of FP whose degree is D, then that's the same as saying F is a splitting field for x, let me write it this way, x to the p to d minus x, which is equal to x to the p to d minus I can factor out the x. So in here, I could just use x to the p to d minus 1. But this one's sort of a little harder to write. So write in a different color. In particular, and part of this, so the only if says that if f is, so if you have a splitting field, then it is of degree d, which means it sort of has p to d elements. So since we know splitting fields exist, we know there is a degree d extension. And we know degree d extensions are exactly sort of the fields of order of FP are sort of the fields of order of p to d. So for every prime power p to d, there exists a field of order p to d. So again, just take the splitting field of this polynomial. This theorem says that that has, we know already that splitting fields exist, and this theorem says that that has degree d, and so by what we consider above has order p to d. So there exists a field of order p to d, and it is unique up to isomorphism. Because if we have two such fields, well, first we know from what we discussed above that they're both extensions of FP. And then each of those extensions of FP is, by this result, a splitting field of this polynomial. And we know any two splitting fields of the same polynomial are isomorphic. Okay, so and this is the precise version of the statement. This is what we'll actually prove, but like and in fact, it's probably better to store this precise version in your head because otherwise you can, well, but like this is sort of the consequence that you sort of commonly see written down. And this is sort of the more conceptual consequences that there's a unique field of every prime order, any prime power, sort of up to isomorphism. Okay. So proof. Okay, so let's do so if f colon fp equal d, then the size of F cross, so let me say it this way, then by the above, we know that F cross is cyclic of order p to the d minus 1, sorry, of p to the d minus 1. Okay, and so that means so every element is a root of, so every element F cross is a root of x to the p to the d minus 1. Minus 1 is equal to 0. I mean, I guess I didn't even need the lemma here. I just need this has order. Yeah, here I don't even need the lemma. Maybe I never needed the lemma. We'll find out in a second. So then F cross has order p to the d minus 1. So every element is a root of x to the p to the d minus 1. Okay, and so in x to the p to the d minus x, so I see, which is just, so I take this thing I had here and I multiply by x. Well, this is just the product over every element of f of x minus alpha. So over all the elements of this field. And why? Well, every element of the field is a root of this polynomial. The units are a root of this first part, by what I just said, and then 0 is a root of the second part. So these are all roots. That means sort of definitely this divides it. But on the other hand, this is degree p to the d, and the field, there are p to the d elements in f. So really these have to be equal. Okay, so, well, but then obviously f is generated by and somehow this is tautologically true that f is generated by the roots of this polynomial, because the roots of the polynomial are just equal to f. So and this is tautologically, a field extension is generated by sort of all of the elements in that field extension. So this is not surprising. Okay, so that's one direction. So I guess that's the if this du's extension has degree d, then f is a splitting field. For this specific polynomial, x to the p to the d minus x. So conversely, if f is a splitting field, well, I'm going to use one fact that we'll see. Okay, I see why I set it up like this. This way I don't have to use the fact. So there are two ways I could do this. Let me do it the way I set up though. So if f is a splitting field, well, f cross is cyclic. So let me write. So okay, so if f is a splitting field for x to the p to the d minus x, well, let me just write k to be the degree of f. I mean, we want to deduce the k is d, but we don't know that. And then what we do know, sort of f across is just cyclic of order p to the k minus 1. So how was I going to do this? Okay, and I think somehow I'm going to use the fact I was trying to avoid saying anyway, so let me say it a simpler way. And maybe I just never use this lemma. This lemma is fun to know anyway. Sorry about that. Well, and the thing to note is, the thing to note is somehow that the roots of x to the p to the d minus x are unique. So, and basically this follows from the fact that the derivative of this is -1 because so p to the d goes to 0. So, and there's this, we'll talk about this next time, but in this condition, you can sort of check whether a polynomial has multiple roots by sort of seeing whether its co-prime to its derivative still holds for an arbitrary field. Okay, and so this is going to tell us that the roots are distinct. So the degree is so then, okay, well, this thing has to have at least p to d elements, so its degree has to be at least d. Okay, and then, yeah, probably I'm still gonna get in trouble here. Probably I didn't do enough preliminaries. So sorry, this was supposed to say is at least d. And then what I wanted to claim is that there is a subfield of order p to the d. And so once I know that there's a subfield of order p to the d, like that will be sort of a splitting, and by the first part, that will be a splitting field for x to the p to the d minus x. Right, but and this is actually, if I just have this condition, this isn't even true. So I should have been more careful here. I mean, somehow, so I should say, okay, sorry, let me just come back to it. I'll come back to it next time. So the point is, so the point from the perspective I was saying is that you in particular know like the units are a cyclic group of order p to the d minus 1, and you know that, or so p to the k minus 1 where k is degree, but you know sort of p to the d minus 1 has to divide that. Okay, well, so anyway, I sort of biffed it. So let me just accept the biff, and I'll come back and I'll do it correctly next time. And there's a slightly easier way to think about this that makes it clearer anyway. And well, we'll do that next time. Sorry for the troubles. I'll stick around for just, I have to go